Le Chatelier's principle states, when the system is disturbed, the system will shift to reduce that disturbance. So what it's going to do is establish a new equilibrium. These disturbances or stresses are due to addition or removal of concentration, increase or decrease of temperature, which affects heat, changes in pressure and volume. Concentration can be molarity or pressure. When something is added as a disturbance, you want to do the opposite. You want to remove it. To remove it, you must shift to the opposite direction. When you remove concentration, you want to produce more of that removal, so you're going to shift towards the removal. Equilibrium constant K is not affected when the concentration is changed. We have the following equation: 2A plus B yields C plus D. To visually see this better, I am going to draw a vertical line to separate my reactants from my products. Right now, this equation is at equilibrium, but what we're going to do is we're going to add stresses or disturbances which will cause the equation to shift. So whenever something is added, we're going to shift to the opposite side to relieve the disturbance. A is added, so it wants to remove the stress by shifting to the opposite side. Equilibrium will shift to the right, and when that happens, my B concentration will decrease because A and B have to react together to remove the A, and my C and D will increase. Here B is removed, so the concentration of B is lower. Since it's removed, we want to do the opposite and you want to increase it. To do that, we must shift to the same side. So when we remove, we shift towards the removal so that we shift to the left. Everything in the reactant side will increase. The product side will decrease because C and D must react to produce A and B. If I add B, B will increase. So I need to do the opposite and I need to decrease B to relieve the stress. So I need to shift away or I shift to the right. So my products will increase and my reactants will decrease. If I remove C, I need to shift towards removal because I need to do the opposite. I need to produce more to relieve the stress. So I'm going to shift to the product side. My products are going to increase. My reactants are going to decrease. If I add D, I need to do the opposite and remove it. So I need to shift to the reactant side. So my reactants are going to increase and my products are going to decrease. If I remove D, I have too little of D, so what I need to do is produce more, which is the opposite. So I need to shift towards removal, which is to the right. So my C is going to increase and my reactants are going to decrease. When I add or remove concentration, my equilibrium constant K or KEQ does not change. It remains the same. It is not affected by the amount of concentration that is removed or added. So for concentration, anytime you add, you want to do the opposite to relieve the stress. So we shift away. When we remove, we want to produce more of it, so we need to shift towards the same side. The side that gets the tip of the arrow increases concentration. The side that gets the back of the arrow decreases in concentration. The second type of stress or disturbance that can be added and removed is temperature. When we have temperature, the first thing we do is we locate the heat, because the temperature will affect how much heat will be transferred. Anything that is exothermic will have a negative delta H or negative enthalpy. It will be located on the product side. Anything that is endothermic will have a positive delta H and it will be located on the reactant side. Once you locate the heat, the shift process is the same as for concentration. So when I add temperature, I'm going to shift to the opposite side. When I remove temperature, I'm going to shift towards the removal. And lastly, temperature is the only time the equilibrium concentration changes. In the following equation, we have A plus B yields C plus heat. Since temperature is decreased or increased, first thing we need to do is locate the heat. Heat is located on the product side here. This is an exothermic reaction. After we locate the heat, we do the same thing as we did for concentration. Temperature is decreased, so there is going to be less heat transfer. So my temperature decreased. We are going to move to the side of the removal. So we're going to shift towards the removal. So I'm going to shift to the product side, or my product is going to increase. My reactants will decrease and my K will change. Remember, equilibrium constant only changes with temperature. General formula for KEQ is product over reactant. So after the shift, there is more products than reactant. K is going to increase. So when the temperature is increased, where there is heat, my temperature is going to increase. So that means more heat can be transferred. So we need to decrease the heat. So we shift to the opposite side. So we're going to shift to the reactants. My reactants are going to increase. My products are going to decrease. Equilibrium is products over reactant. Since there are more reactants and the reactants is a denominator, my K is going to decrease. In the second equation, we have heat plus A plus B yields C plus D. We're going to locate the heat. The heat is located in the reactant side. So this is going to be an endothermic. And then we're going to shift accordingly as we did with concentration. When there's a decrease in temperature, less heat is going to transfer. So the heat is being removed. We shift towards the side of the removal. So we're going to shift to the reactant side. So my reactants are going to increase. My products are going to decrease. My equilibrium is still equal to products over reactant. Since there are more reactants and the reactants are the denominator, my K here is going to decrease. When the temperature is increased, we're adding more heat. So we're going to shift away to establish new equilibrium. So we're going to shift to the right or the product side. So my reactants are going to decrease. My products are going to increase. My K is going to increase because now there are more products. For Le Chatelier's principle, when you solve for temperature, first thing you do is you locate the heat. After you locate the heat, you shift like you did before. If you add temperature, you're going to shift away or to the opposite side. If you remove temperature, you're going to shift towards or shift to the same side. Remember, when we are doing equilibrium, we are always doing the opposite. Pressure is another stress or disturbance that can be added or removed. First thing you do is you count the moles of the gases. The only thing that exerts pressure is the gas state. So you must look at the subscript. Solid, liquids, and aqueous do not count. To decrease the pressure, you shift to the side of less moles. If you increase pressure, you shift to the side of more moles. You will be applying Boyle's law here because sometimes pressure will be increased or decreased, but sometimes volume will be given as increase and decrease. According to Boyle's law, pressure times volume is a constant, and this tells you that pressure and volume are inversely related. So if the volume is small, the pressure is going to get large and vice versa. The volume is constant or inner gases are added to the system or removed from the system, there is no effect or no shift in the equilibrium. In addition, pressure does not affect equilibrium constant, only temperature does. So in the following equation, we have 2A plus B yields C plus 3D. So here we have the pressure is increased. When the pressure is increased, what we want to do is the opposite. So we want to decrease the pressure. To decrease the pressure, we need to count the number of moles on the reactants and the product side. On the reactant side, we have 2 moles. B does not count because it's in the liquid state. Only gases count when we are discussing pressure. In the products, we only have 1 mole because D is a solid, so it does not count. The pressure was increased, so what we want to do is we want to decrease the pressure. To decrease the pressure, we shift to the side of least moles. We're going to shift to the right. The reactants will decrease and the products will increase. Next, the pressure was decreased. We want to do the opposite to reestablish equilibrium. That means I need to increase pressure. To increase pressure, I want to shift to the side with most moles, which is the reactant side. So my reactants are going to increase and my products are going to decrease. When the volume is increased, we think of Boyle's law. Boyle's law said pressure and volume are inversely related. There's an increase in volume. The system itself has a lower pressure. So to establish new equilibrium, we need to increase the pressure. To increase the pressure, we must shift to the side with more moles. So we're going to shift to the left. My reactants are going to increase and my products are going to decrease. When the volume is decreased, we know my pressure will increase according to Boyle's law here. So we need to do the opposite. We need to lower my pressure. To lower my pressure, I need to shift to the side of least moles. That is the product side. So my products are going to increase. My reactants are going to decrease. If I add argon, argon is an inert gas. It is not part of this equation. There is going to be no change, or it's going to remain the same, one or the other. If I remove helium, again, helium is not part of this reaction, so there is no change. In addition, K equilibrium will stay the same. Equilibrium constant only changes with temperature. Catalyst. In the previous chapter, we learned catalyst speeds up reaction by lowering the activation energy by providing an alternate pathway. When I add a catalyst to the system, there is no effect on the equilibrium position. That means catalysts cannot shift the reaction, cannot change the equilibrium position. In other words, it can only speed up the reaction. Pause the video, complete this table on your own, and then check your answer. So we have 3H plus K yields M plus 2A. First thing I'm going to do is I'm going to separate the reactants and products so it's a little bit easier to see. I am adding H. When I add H, the H is going to increase. Since H is a solid, it will not change the equilibrium position because solids and liquids, their concentration remains the same. If I remove A minus, my concentration of A is going to decrease. To relieve the stress, I need to produce more A. To do that, I need to shift towards A. So I'm going to shift towards the product. M2 plus is going to increase. My K and H are going to decrease. My K remains the same here. No change. If I add M2 plus, this is going to increase. To relieve the stress, I must go towards the opposite side. So this is going to shift towards the reactant side. So my reactants are going to increase. And my products are going to decrease. My K will still stay the same. If I increase pressure or decrease pressure, the first thing I need to do is I need to count the number of moles. On the reactant side, there is only 1 mole because H is a solid. Only K is a gas. On the product side, I have 0 moles because both of my products are AQ. So if I increase the pressure, I need to do the opposite. I need to decrease the pressure. To decrease the pressure, I need to go to the side of the least moles. So that means I must shift to the product side. So my products are going to increase. My reactants are going to decrease. My K is going to be the same. If my pressure is decreased, I need to increase my pressure to reestablish equilibrium. To increase pressure, I need to go to the side of more moles, so that is the reactant side. So my reactants are going to increase and my products are going to decrease, and my K again will stay the same. If I add K, my K concentration increase, so I need to remove it by shifting to the opposite side. So I'm going to shift to the product side. My products are going to increase, my reactant is going to decrease, and my K is going to remain the same. Pause the video and complete this table and then check your answer. Again, I'm going to draw a line to separate the products and reactants. First stress we're adding is we're increasing temperature. When temperature is given, first thing we do is we locate the heat. Delta H is provided as positive, therefore I know the heat is on the reactant side. So I am increasing the temperature. So if I increase the temperature, that means that the heat is going to be increasing. So to relieve the stress, I need to shift to the opposite side. So it's going to shift to the products. My reactants are going to decrease. My products are going to increase. And my K is dependent on temperature. And K we stated was products over reactants. Since we have more products than reactants and the products are the numerator, my K here is going to increase. In the second one, there's a decrease in temperature. So my temperature is decreased. So when it's decreased, we want to increase it. So we're going to shift towards the removal. So that means we're going to shift towards reactants. My reactants are going to increase. My products are going to decrease. And my K is going to decrease because there is more reactants, and the reactants are denominators. Next one, there's an increase in volume. So the first thing I need to do, if it's volume, we're talking about Boyle's law, and we know pressure and volume are inversely related. So first thing we need to do is count the number of moles. In the reactant side, there is 1 mole from the K. H is a solid, so it doesn't count. In the product side, I have 0 moles because both are aqueous. So when the volume is increased, that tells us that the pressure has to be decreased because they are inversely related. Since the pressure is decreased, I need to do the opposite to relieve the stress by increasing the pressure. To increase the pressure, I need to shift to the side with more moles, that is to my reactant side. So my reactants will increase, my products will decrease, and my K is the same because only temperature changes it. When the volume is decreased, according to Boyle's law, my pressure is increased because they're inversely related. So that means I need to do the opposite again. I have to decrease the pressure. To decrease the pressure, I go to the side of these moles. So that means I need to shift to the product side. My products increase. My reactants decrease. My K remains the same because only temperature affects it. When I have catalyst, there's no effect. I told you catalyst only changes the speed of the reaction, which is kinetic. When I add neon gas is inert, it's not part of the reaction, so this is also no effect. Le Chatelier's principle is pretty easy. What it does is if a disturbance is present, the system will shift to establish new equilibrium. There are 3 main stressors or disturbances. They are concentration, temperature, and pressure. For concentration, when you add, you shift away to relieve the stress, to get rid of it. If you remove, you want to shift towards because you want to produce more of it. Temperature is done exactly the same way, but the first thing you need to do is locate the heat. When it's endothermic, it is in the reactant side or the left side, or it's a positive delta H. If it's on the product side, it is exothermic, negative value delta H, or on the right side. After you locate the heat, you shift just like you did for concentration. For pressure, you must count the number of moles for only gas. You always shift to the lower moles to decrease pressure, and you shift towards the higher moles to increase pressure. If volume is given, you must apply Boyle's law. Pressure and volume are inversely related, but the shift is the same for the pressure. When catalysts, inert gases, no change in volume are given, no shift in the equilibrium. In addition, solids and liquids will not provide a shift in the equilibrium.